So here we are at the Arizona EEC, that's the Energy Education Center. And to the right hand side, you can see an example of a dry storage cask container. And it's actually quite interesting. We're going to take a closer look. There's a sign that tells you all about what this is about, and I'm going to read it while I pan around and show you. It says, "Safe and secure storage. This robust, highly engineered steel and concrete container is one of the systems used for dry cask storage and provides safe and secure storage of used fuel assemblies. Fuel assemblies that are no longer productive for use in Palo Verde's reactors without additional processing are known as used fuel. Palo Verde stores used fuel during a two-step process. First, the used fuel spends several years immersed in wet storage on site in a fuel pool where it cools. Second, and after initial cooling, the used fuel is placed in dry storage using dry cask storage as we see here. Each dry cask system manufactured by NEC International can store 24 to 37 used fuel assemblies in a basket holder inside a steel-lined transportable storage container with a welded steel lid. The canister is then surrounded by vertical concrete cask rebar, which you see here, concrete overpack, and a concrete lid. Air vents help with cooling, while a lift lug helps during transport. The loaded canisters stand upright on a monitored and secure concrete pad where they are safely stored until a long-term storage facility is licensed by the Department of Energy. The Nuclear Waste Policy Act of 1982 directed the federal government to develop a national site for used nuclear fuel and a high-level radioactive waste storage." So here's the entranceway to the Palo Verde Energy Education Center. And we're going to take a quick look at this over here as well. It says, "Water in the desert." And this is actually one of the very interesting things about the Palo Verde plant. It says here, "You are standing in front of a cross-section of the same pipe used to transport wastewater to Palo Verde through 36 miles of underground pipe from the 91st Avenue and Tolson wastewater treatment facilities. Instead of using valuable natural resources, and by that we're referring to water, Palo Verde purchases 20 billion gallons of wastewater effluent annually from Phoenix, Glendale, Scottsdale, Tempe, Mesa, and Tolleson." So this is the only plant in the world that actually uses wastewater for cooling instead of just being built next to a pond or river or something like that. Now we actually have a visit scheduled here for 1 p.m. and we're just a little bit early, so I'm just going to show you the signs. Anytime you want to come visit, you simply give them a call. You can arrange a group experience or visit on your own. The number is 623-393-4699 or to PV, that's Palo Verde, exhibits at apsc.com. And it says, "Group visits to the Energy Education Center are customarily conducted on Tuesday and Thursday each week, along with the first Saturday of each month throughout the year. Protons have a positive charge, electrons have a negative charge, and neutrons have no charge. Visiting the Palo Verde Energy Education Center is like neutrons. There's no charge and admission is free. Safely and efficiently generate electricity for the long term. Palo Verde." On the other side, we have a welcome. "Welcome to Palo Verde. Welcome to Palo Verde Energy Education Center. I'm going to do it again. Welcome to Palo Verde. Welcome to the Palo Verde Energy Education Center, the only facility of its kind in Arizona. We're glad you're here. Start your unique experience by visiting our outdoor exhibits featuring dynamic displays related to dry cask storage and energy comparison of nuclear to fossil fuels and our innovative environmentally sensitive use of water in the desert. Continue your unique experience inside the center to learn more about Palo Verde Nuclear Generating Station and nuclear energy production around the world. Innovative exhibits provide a virtual tour of the nation's largest power producer and show our innovative use of reclaimed effluent, that's wastewater. You'll also discover more than a century of history related to nuclear energy and Arizona's only nuclear energy facility. Stand over a simulated reactor core Learn how Palo Verde uses the power of the atom to safely and efficiently produce electricity delivered to homes and businesses in Arizona and across the Southwest, and much more. You'll also learn about nuclear safety. You will also learn about the nuclear professionals at Palo Verde and how these dedicated men and women work safely each day to efficiently generate electricity for the long term. Well, let's see if this is locked. Nope.
We have it in a very controlled fashion, and with that concentration of those control rods, that allows us to bring it up in a nice controlled fashion all the way to 100% power. Makes sense.
Drilling today, Rick?
Say what? No.
Were you drilling today?
No, this is my nephew Brendan. He was out talking to Lindsay Paulson. He was interviewing for an internship job for next summer.
How you doing? Mark Fallon.
Brian, nice to meet you.
Pleasure.
He's our leader in our strategic communications group, so it's kind of their baby.
Oh,
So,
cool.
yeah.
Hi.
Hi.
My name is Brett Walters.
Oh, I'm Mark.
Hi.
You're
Brett
going
Redmond.
to meet me.
I'm here to meet you. Huh?
You're early.
I am a little early. Sorry about that.
Okay. And it's just you?
Yeah, at this point it is. And
Yeah.
do you mind if I film some things?
No.
I don't think it was a problem.
Just go ahead and help yourself looking around. It's all pretty self-explanatory, but I can answer any questions you have.
Do you mind if I film you while you do the introduction?
No?
Okay, great. So just give me your name and say
Well,
hello.
tell me what it's for.
This is for basically YouTube and for, we're working on a documentary for nuclear power.
Yeah.
And if it makes you feel any better, this is a pro-nuclear power documentary.
Yeah, I don't know about the YouTube thing. That's. Well, let me think about it.
What I want to do is I want to make sure that people know about this place
Yep.
and come to visit it.
Yep.
And also I plan to give you copies of several of the pictures that we're taking as we go by because
Okay.
I visited the various sites that talk about this place.
Mhm.
There's nothing. There's
No,
information.
we just opened.
See, exactly.
Yeah,
so I
so-
figure if I give you some pictures and other information, it helps you as well.
Okay. So I'll just show you around real quick, and I'll let you look around, and then we'll talk about doing something
Okay.
with me. A lot of these are touch screen, so you can see I had to touch it to activate it. And this is basically a timeline of nuclear history. So a lot of it is U.S. and world history as it starts out, and then when you hit the 1960s, you'll enter the era of Palo Verde. It started with the formation of the study group, and so then you'll have concurrent running timelines for U.S. world nuclear history as well as Palo Verde history.
Okay.
All right.
And is there any talk about, let's see what we have here. It's for peace, good. There's the first nuclear submarine launch.
Yeah, it covers pretty much in depth the history of nuclear power.
And there's the first reactor, Fermi, good. And is there any mention of the alternative nuclear technologies being explored for Generation 4?
Not yet. But
Okay.
it's probably something that we'll add at some point. So if you go down, that's kind of in the. At least I don't recall adding it in here. So Yucca Mountain,
There's an upgrade, that's nice.
Blue Ribbon Commission being formed.
Mm-hmm.
So it would be in this time frame, but we haven't added any of that information as yet.
Okay. And then how far do we go?
Just to right here, to the end of 2012. We'll be adding some 2013 information as well as some additional.
I see. No, that's interesting. All right, let's take a look at some more.
On the other side, you've got information about where nuclear plants are in the world, what percentage of generation is nuclear versus other technologies. So the United States with 100 units, a little less than 800 billion kilowatt hours, about 19.2% of our total generation.
I see.
But comparatively, France has 58 reactors, which generate 77.7% of their capacity. So smaller load, obviously, in that country. But so you can see again, you got countries like the Czech Republic, 33%, but it's only 6 reactors, 5 reactors, and Switzerland meet almost half, a little less, 40.8%, so on. So it's varying degrees of percentage and varying degrees of reactors in the various countries, with U.S. having significantly more than any other country.
Now, ever since Fukushima, there's been a backlash about negativity, basically, in reactors, especially in Asia.
What's interesting is that that's not necessarily true.
Okay.
The Chinese have 19 or 17 reactors currently. They have another 29, I believe, is the number under construction, and they're looking to build as many as 300 reactors over the next few decades.
So China's not affected by the Fukushima attitude. What about Japan?
Japan is obviously up in the air.
Okay.
Not sure what'll happen. They in my opinion, economically, they're not going to be able to survive without nuclear, and so they are the latest headlines have them reopening some of their undamaged nuclear facilities. In reality, Fukushima Daiichi, and there are 2 Fukushima sites,
right,
is the only site that was actually damaged by the earthquake and tsunami. And in fact, the issue was not the earthquake; the issue was the tsunami that followed.
Right, and Fukushima actually was a very badly designed, maintained reactor in that sense.
Yeah, I wouldn't say the initial design was bad. I think the upgrade of that design, and continued improvement of that design is questionable, and certainly their regulatory oversight of their country's reactor is certainly brought into question as well.
Okay.
This is a digital representation of the site at Palo Verde, so you can see the site here digitally from various angles, whatever you want to look at.
You just zoom in on something, or you pick the name?
So you can pick the name if you want over here, and it'll zoom in and tell you then a little bit about that part of the site.
Okay, so right now we're looking at the switchyard item.
And so if you hit back, then it goes back to the full view. But you can drill down in the same manner without touching the name, by touching the structure or area of the site.
Oh, interesting. So maybe let's take a look.
For example, this is the turbine building.
Okay.
But if you look, I touched on that particular building, right? But if I go over here and if I do the main cluster of buildings, it will identify each of those independently, and then you can click on the containment building, and it'll...
No, this is a really well done system you've got going on.
So it basically gives you the general layout of the site and the main structures and operational mechanisms of the site.
So let's have a look at the reactor.
What?
Yes.
The containment building.
Okay. And can you drill down any further than that?
No,
or we need to look
not at this point.
Okay, so let's continue then.
So we have here in essence what looks like the reactor. So if you look down into the reactor, you would see the fuel assemblies, 241 fuel assemblies in the reactor.
And this is an example.
And this is an example of what a fuel assembly looks like.
Okay.
There are 236 pins or tubes that have the fuel pellets in them that make up a fuel assembly, and there are 241 fuel assemblies that make up the reactor fuel load.
Interesting.
Also sometimes commonly known as the core.
Okay. So this is the, I guess you could say, example core that you can walk on and see what it would look like physically as size basis.
Yep. It's slightly smaller in diameter than the actual reactor, but not terribly small.
Okay, so close to the real size.
Yeah, it's in close proximity to the actual size.
So that's really quite amazing when you think about the fact that about 1.4 gigawatts
Yeah,
EEC
each
power
unit, each unit is capable of about 1,420 megawatts, 1,420 megawatts,
Okay.
or enough energy to serve about 1.5 million people.
And this is, of course, the, I guess, introduction for what we're walking on and looking
Correct.
at. Okay, let's take a look at that side.
This is, in essence, what is a mock-up of a containment wall structure. So you can see the rebar and the post-tensioning tubes that are both horizontally and vertically throughout the walls. The average thickness of the containment walls is about 4 feet. So they are, in fact, about this thick.
And what would these discs be representing?
These are corrugated steel tubes that are in the walls that then have a bundle of steel rods in them that are then locked in at each side and twisted to about 1 million pounds pressure.
Okay.
So it's called post-tensioning.
Okay.
Walls are pre-stressed and post-tension and in about 4 feet of concrete, you get the equivalent strength of about 35 feet of concrete and steel.
Okay. Now, just to let you know, I've been keeping your face off of
That's
this
fine.
so that probably that's okay.
Yeah.
Do you mind if I put your hands in there when
No,
you're
that's fine.
doing
No,
your
no, it's
motions? Okay. So, hi.
This, you can see here, this gives you some detail about sort of the structure and engineering of the containment building and the components inside. So you have the reactor coolant pumps that move the water through the system, the steam generators, and the pressurizer, which are the main components inside the containment building. Inside the building, you have a steel liner, about 1/4 inch thick, welded steel liner. Provides an airtight structure. You have then the rebar that is laced throughout the concrete, and again the heavy approximately 4 feet of concrete that overlays that. The base mat of the building is about 10 feet thick, concrete and steel.
Now, what's the purpose of having it be so thick? Is that for vibration? Is that in case there's a leak? What's the
No,
idea?
its title tells you what it's about. It's a containment building.
Okay.
So it is built to contain the nuclear material within under any and all conditions, be they external pressures or internal pressures. So if you were to have high temperature water that flashed to steam in here, the pressure that would ensue, the building is built to withstand that. It is also built to withstand external pressures like natural events, airplane crashes, those kinds of things.
What happens to the steam in such an event after the flashing has occurred, and I'm assuming it's cooled back down again?
Yeah, so what you have is up in the top of the building rings of what look like and really aren't much different than fire sprinklers. And so they would spray cooler water in there to knock down that pressure by knocking the steam and cooling it back down to water. There's a sump in the bottom of the containment building that would then drain off that water, or it could be controlled.
And then what would happen to that water?
Like any water that's potentially radioactive, it would be cleaned up or sent through evaporators, evaporating it off to just a dry waste.
Interesting. Yeah. And what do we have behind us?
Just a little exhibit about our community partnerships, so donations to local charities through volunteerism, the $1.8 billion of economic impact that Palo Verde has on the state of Arizona. And
isn't this the largest business impact in the state of Arizona?
we're the largest single taxpayer in the state of Arizona.
Interesting.
$50 million a year in property taxes alone.
Okay.
And of course, the part of that that's probably even more important is the clean, reliable, and cost-effective electricity that we provide customers across the western United States.
Well, thanks to Palo Verde, Palo Verde is providing about 35% of Arizona's energy needs?
It's around 30%.
30%?
Yeah.
Okay. And compare that to the 19, almost 20% across the U.S.
It varies by state. It can be lower. Obviously there's some states that have no nuclear power plant, so it would be zero.
Which is unfortunate.
On the average across the United States, it's between 19 and 20% each year, generally speaking.
Okay.
In Arizona, it's a little larger because we have two of our owners.
Go ahead.
So two of our owners are Arizona utilities, being APS and Salt River Project. So
Okay.
with their percentage of ownership, so you can see the owners over here, APS and SRP. APS owning 29.1%, Salt River Project about 17.5%. But then you also have owners like El Paso Electric in Texas, Southern California Edison, and Southern California Public Power Authority, and Los Angeles Department of Water and Power in California, and Public Service Company of New Mexico, obviously in New Mexico.
And it says this generation station serves more than 4 million people across Arizona, California, New Mexico, and Texas.
That's correct. So it's, in essence, it's the amount of electricity that goes to any one population of people in any of the utilities is based on the percentage of ownership.
Okay. We have a discussion here about safety.
Yeah, and you'll see safety as a discussion throughout the facility.
Not too surprising, since that and waste tends to be some of the biggest public questions and concerns.
So this exhibit is related to training. And so through these iPads, basically, for whatever career, be it maintenance or engineering or radiation protection or nuclear operators or security, you can explore who I am. Not this particular person, but an engineer in particular, what they do. So what are their normal activities? How did I get here? So usually it's talking about their educational background and expertise coming in. And then continuous training, which all of our various job positions out here have, that talk about the annual retraining and sometimes relicensing that some of these basic positions might have to go through.
So this wall would be great for anyone who's thinking of becoming involved in nucler power, maybe as
so
an
not,
employment.
so not only is it a training exhibit in that it talks about the ongoing and continuous training that people get, it's also talking about sort of the variety of jobs and what it takes to get one of those.
Excellent.
We do have the exhibit on radiation. A lot of very basic information. Thing here that tells you what kind of things surround us every day that might be radioactive, like crushed landscaping rock, of course, X-rays everybody is familiar with.
Bananas.
The granite countertops.
Yes.
Other medical procedures such as CT scans, which are quite common, it seems, these days. Water softening pellets, the food and water, and smoke detector. Some of the common things that people have come to know. We also have an iPad-based calculator that you can go through, and you pick the state you live in, and it'll tell you the background radiation that you can expect living in that particular region of the country, what kind of home you live in, whether it's wood, adobe, brick, stone, whatever it may be. For a stone home, it's 7 millirem a year. Living near a power plant, it's actually higher for a coal plant than it is a nuclear plant.
Now that's a really interesting thing. Why is the coal plant more radioactive than a radiation?
Because in the mine coal, there will be radioactive material in that coal that's when it's ground up and sent into the boiler, that radioactive material will be in the emissions of the plant. Flying gives you a significant amount, depending on the amount of times you fly. Probably the average person probably takes 7 or 8 flights a year. Average flight typically is something on the order of 3 to 4 hours. So then you're talking about 32 millirem a year from cosmic radiation by taking flights.
So are you familiar at all with the measurement of millirems and what it means as a person? Like, how does it change your rate of cancer? How does it, what is your real risk?
Yeah, the risk associated with it, of course, goes up as the amount of radiation goes up. The average American, according to studies, gets about 620 millirem per year, which is well below where you would expect to see biological, physiological changes in the form of cancers or other issues.
And what this display is basically saying is there's much greater concerns of radiation from other things other than nuclear plants. And
yes and no. What it's saying is radiation is around us every day in our everyday lives, and it's not. What we're showing here is that not that you should be concerned, for example, about having a CT scan, because the doctor's ordering a CT scan because they're either wanting to discover or treat you for some ailment that is of much greater risk to you than the exposure associated with that short-term exposure.
Right. So at the same time as showing that the nuclear plant is basically releasing almost no radiation compared to your surrounding environment, the surrounding environment isn't even that strong in radiation to begin with.
Right, and it depends. If you live in Denver, Colorado, which is a much rockier terrestrial radiation environment, or you live and you're at a higher altitude, your exposure from those natural sources is going to be higher than they might be, for example, in the Phoenix area.
Understood.
So a lot of medical exposure potentials, both from X-rays and the more common things to the CT scans. For example, if you got a chest CT scan, you're talking about 700 millirounds, so it's pretty hefty. And so in this case, where I just sort of made some things up as I went along, this person would look at 1,081 millirem for that year, which is 174% of what the annual expected exposure for an American might be. But the likelihood is they're not going to have that CT scan every year, though, so it'll probably drop back into the normal range. When I do it for me, for example, if I follow what is truly what I see, it would be below the national average. And typically what you'll see is the older Americans will have a higher number than the younger Americans, because the younger Americans aren't getting a lot of X-rays and other medical exposures that are associated with growing older, right?
Probably less flights too.
Yeah, so only a few years ago, the average American was estimated to be 360 millirem. Now it's 620, so it's doubled. And most of that is in regard to medical treatments associated with older Americans.
At 620 millirems is still basically almost nothing as far as its effect on the human body.
That is correct.
And do we have any kind of studies we can reference or something that says that there's very little effect?
Yeah, there are a number of studies. I think it's the National Academy of Sciences. I'd have to go find it, but there are a couple of studies that show that where you would expect to see biological damage or biological issues, physiological changes is much, much higher than that. And of course, we have information on emergency preparedness and planning. This building is part of that emergency preparedness plan, in that it is also where we would gather to do off-site emergency response, and where we would brief the media on what might be happening at the plant, both us, state agencies and county agencies, as well as potentially the Nuclear Regulatory Commission would gather to take care of that.
So we have this example of, I guess you could say, exclusion zones and so forth, or concern zones. But
emergency planning zones.
Okay.
Yeah.
So how severe would an event have to be in order to have to make any kind of alert?
Well, there are 4 layers, there are 4 levels of emergency declarations in the industry. And, if you get into a notification unusual event, it can be something very simple, that it creates no issue or even a potential hazard to the public. At an alert, you're getting into a little higher criteria, but you're not releasing radioactive material from the plant in numbers that would be associated with impacts to anyone in the surrounding areas of the plant. And then in the higher 2 levels, you have the potential or real release of radioactive material from the plant, which would cause you to take some protective actions within the 10-mile radius.
Okay. And most events wouldn't even trigger something of that significance. Like, let's take an example of the flashing to steam, which would be ridiculous in probability, but it's still all within the containment building. What kind of alert would that generate?
I'd actually have to go into the procedures and check, because it's very finite in our operating procedures and our emergency response procedures when X happens.
Right.
Because there are any number of variables. But I'm not. I would hate to give you an answer and have it be wrong.
Fair enough. We can look at that later.
So this is a nice cutaway of what the plant looks like inside. Very simplified version, which has again the reactor at the center here, the fuel within, which is you've seen at the reactor model over there. Reactor coolant pumps, which move the water. Steam generators. That then moves steam over here, which drives the turbines, which turn the generator, and then the steam is condensed in the condensers, so it can be returned to the steam generators. And then we have our cooling towers that are the final loop.
So I'd like to learn a little bit more about the cooling towers. Since Palo Verde is not near any kind of, shall we say, major water sources like lakes, oceans, rivers, etc. This is the only plant in the world, to my knowledge, that uses the method of using effluent for coolant.
Currently, there are plants under consideration, in particular in the Middle East, that are exploring also use of sewage effluent as their cooling, as are a couple of other facilities in the U.S. potentially. But as it currently stands, it's the only facility I'm aware of that's using sewage effluent as its cooling water.
And we'll learn more about how that's possible.
Yeah, I mean we have a whole exhibit back in the front that deals with cooling water. So
great, we'll take a look at that.
So this is a nice digital, constant running cutaway, if you will, of how the plant is operating. And here you can actually see the cooling towers, and in a moment. So as part of that, it does talk about water vapor evaporating off the top of the cooling towers, about 18,000 gallons a minute per unit. And it's basically just environmental evaporative cooling that's taking place of that water. The water is coming in around to the cooling towers so now it's starting back over again. So you talked about, did that one model go into containment? No, but this one does. So within that, it'll start now cutting away into the various things, showing the flows of water and heat inside those systems, and it'll follow it through the 3 loops of a pressurized water reactor, which are in a simpler form shown here, and then a boiling water reactor, which is not the type we have, but we use the pressurized water reactors. But those are the 2 predominant designs worldwide.
Where do you find boiling water reactors?
Boiling water reactors are in use throughout the world. There are some in the United States, although the larger number in the United States and throughout the world is pressurized water reactors.
Would the CANDU type of reactor be a boiling water reactor or no?
I don't believe it is. I don't really study the CANDU reactors. Those are Canadian design. We don't employ those here in the United States.
What about the RBMK from Chernobyl?
Those are quite different. Those are carbon moderated versus water moderated. So in this diagram, where you see these flows, and that surrounds the reactor fuel is water. So water is the moderator and the mechanism by which we move heat. Whereas in those Russian designs, they're using carbon versus water.
It also seems to have a brief word about where uranium comes from. Mm-hmm. Does this discuss